Yeah. All right. I'm live. All right. Hi, guys. Hi, everyone. I'm Andreas Evers. Today I will talk about microservices. Who of you has actually worked with microservices before? Yeah, that's about 50-50. All right, cool. So today it's going to focus on what are microservices and why should we or shouldn't we do microservices. Okay. So I think to really understand microservices, the architectural style, and why we should do it or shouldn't do it, we have to go back in time. Boom. Right. You all know this movie, right? So let's go back to 1970. Who was programming in 1970? My God, you're all new kids. Back in my time, right, we were doing mainframes, third generation computers they were called. Okay, and we had great processing power and storage for that time, relative, of course. Probably your cell phone now has twice that size or maybe 100 times that size, I'm not sure. So we had these big monolithic architectures to run on these big systems. Okay, so that's where we actually come from. Well, in 1960, we even had Bondscards. Is that in English the same word as in Dutch? Bondscards, punch cards. I don't know. These guys were kind of automated with processing power. Right, so let's skip to 1980. Wait, yeah, so this is the kind of boxes and arrows diagram. I kind of have a lot of boxes and arrows in this presentation, so get used to it. This is the first one. It's pretty simple, right? Has a mainframe, some data store in there, and you have some thin clients that could connect to it. Okay, so 1980, the rise of the microprocessors. So Intel invented the first microprocessors, and they quickly became very, very common. And here you can see the Atari, first personal computer system. And these microprocessors allowed companies to build computer systems without having to buy these huge monolithic mainframes, which were very expensive at that time. Okay, so with these microprocessors, we had smaller computers, and we had limited processing and memory capabilities, of course. We didn't have this very expensive machine anymore. And we also had to kind of look into how we could use multiple of these computers together in a network. Hence, distributed computing. Okay, so this is kind of where microservices, which is a very distributed style, kind of comes from. And back in those days, we used RPC technologies, remote procedure calls. Right? Who's familiar with this? Remote procedures? Right, cool. But you probably used you probably all used this kind of technology before, but you might not know it. The idea here is that in your client application, you have client functions, and these functions, they call a client stub. This stub connects over the wire to another stub on the server, which then translates it in another method. So kind of what you have in your code is you just call a method, and it acts like a local call, right? So you don't even notice that there's network underneath, okay? So this was kind of common in these days, and we started to see such an architecture. We now have a database, we have a couple of servers, and they are distributed. So they are they're not exactly on the same, or not necessarily on the same computer, and there's network in between. Okay, and how they actually communicate is over binary coupling. So binary because they have these method calls, these method abstractions. So kind of a lot of that's actually heavy coupling because you're coupled to the syntax, to the signature of the method. Okay. So let's skip to 1990. Okay. So here we see the first. Well, who knows this computer? Anyone has seen this? There's kind of a hint over here. CERN. This is where the internet was invented. Okay, the first computer that ran the internet. Okay, I think, what was it called again? I think it's called Nextcube. So this is a kind of more powerful computer. So it kind of allowed people to run more sophisticated programs, also in a distributed environment. But we kind of started feeling that while we were doing this distributed computing, that we kind of didn't always need to run it in a distributed fashion, that we could actually just run it on one computer, and that was probably better. We would probably be better off not having this network complexity in our code. Okay, so this is kind of the next step for RPC, Corba. Who's worked with Corba? Come on, at least one guy, 2 guys, 3. Yeah, that's great technology, right? Corba. Corba is just the same as RPC, basically. You also have the binary coupling there. We started seeing EGBs. EGB 1.x, so 1.0 and 1.1. And that was kind of difficult because you were stuck to Java with EGBs. And there was a lack of interoperability. So that's kind of a downside if you want to have different systems communicating with each other, obviously. So our architecture kind of started looking like this. Same kind of setup, lots of servers, but now they were talking to each other over binary coupling a lot more. Okay, and with EGB2, this became a lot worse. Okay, so if we look at 2000, the internet became more popular, okay, more widespread. And there we saw that there was a movement towards a more structured approach. This approach was called the service-oriented architecture. Okay, this is often combined with a central ESB. Okay, the lovely ESB that kind of couples everything together. We also had shared database access, which was deemed a good thing back then. And we were using web services. Okay, so these services in the service-oriented architecture, they exposed a couple of web services over SOAP, and SOAP was then using network protocols such as HTTP or SMTP. Okay, and as you can see here, the schema kind of tells the same story as RPC. Although SOAP is a more loosely coupled way of doing RPC, but it's still kind of RPC. As you can see here, you still have the client's objects. It's actually kind of, it's the same thing as the previous thing with Corba, but now you have client SOAP handler in between. So if you use Access, anyone used Access? Access 2? Okay, or CXF, right? Always the same. Yeah, then you've seen that actually you have a contract first or contract last approach. Basically, you get a contract, and you get a library, a client library for this contract. This library is then injected or included in your source code, and this kind of couples this service with this service through this contract, and you couple it completely. Okay, so all the fields, even if you only just need one, you couple to all of them. Okay, that's SOAP. That was already using XML as an abstraction, which was an improvement compared to binary coupling in Corba, for instance. But still, if you use the client libraries, you kind of still have binary coupling, right? And whether it's transferring this over binary protocol or over XML, I mean, come on, it's kind of the same thing. Okay, so you kind of have that coupling there as well. So if we go look at the architecture here, we now have an integration bus, the ESB, okay, Enterprise Service Bus. And we have full contract coupling of all services. So this is already more structured, gives you more governance. You see all the interactions through this bus. The bus allows you to do a lot of things, right? It wasn't just messaging, but you could also get like transformations, ETL stuff in this bus. Okay, so all this stuff was going on here. So that was, for a while, a good approach. Wait, let me go back. But we saw that this was quickly becoming a single point of contention. So all the teams of all these different services, they kind of wanted to get stuff done in the ESB. And, well, not all of these teams had access to this ESB. Not all of them were capable of changing things. Obviously, it would just be a complete mess otherwise. So you had this one big ESB team who was allowed to make changes, right? But it was never big enough, right? Because this was a very scalable model. You could get lots more services here, and all these teams kind of needed this one team to do changes. So all these activities needed to be planned, need to be synchronized with the planning of these guys, and you could imagine that your release cycles would be humongous, right? You just get like you make a change request, and it would take like 6 months. Okay, so this model wasn't built for quick releases, but it still gave you a lot of governance, which is a good thing. So, 2010. Well, the 10s, including now. Microservices, okay, disruptive speed. You probably all know these companies, right? They came in the market and they kind of disrupted the entire market just by using a different IT approach. Okay, IT is central to all these companies. You might not know it from Tesla. I think it's like just an automotive company, but the way they use IT is very differentiating. Like for instance, the AI they use for autopilot. That's something completely different, or at least it's much more invested in there than traditional automobile companies. Okay, so that's really a big differentiator. In Uber, everyone knows Uber. They don't own any car, but they're the biggest taxi company in the world. And for Airbnb, they don't own any hotels or beds. They're the biggest accommodation company in the world. And Netflix, well, you know Netflix, right? They're huge, because actually Netflix, they used to send DVDs in the post to you, actually. So you would just receive a letter with a DVD inside. They kind of stopped doing that model. But still, you can imagine that they came from far and they just started taking over the world by using IT, by using streaming. Okay, so all these companies, what they have in common is that their IT is capable of changing very quickly. They have a very disruptive architecture, a very disruptive way of working with services, for instance. And they often do this with microservices architecture. Okay, so 2010 kind of came with some observations from the past. And with all this RPC stuff that we were doing, everybody kind of found out that when you make a distributed call and you try to make it look like a local call, that just doesn't work. Okay, don't try to kind of use some client library or something. That just doesn't work. You'll always have the network complexity. You probably know the 8 or how many fallacies of distributed computing, right? They are there. They're real. Okay, so distribution is difficult, and trying to abstract that in a local call is just not going to work. Okay, so this kind of architecture, which we'll see today, is a very decoupled architecture. Decoupling is central to microservices. Okay, so you have high cohesion and low coupling. It's kind of a design pattern everybody knows, but it's applied to architecture in a very strong way. Also to the data, and that's where things get difficult. Okay, if you split your service in multiple parts, it's pretty straightforward, but your data, when you cut that up in pieces, that's where things get rough. Okay, so we'll see that in the next part of the presentation. And obviously, next to your data and your services, you also want to split your teams along the same lines as your services are split. Okay, we'll also talk about that later. Okay, so these are kind of styles, or at least an architectural style that is introduced in 2010 and is now becoming very common. Okay, so if you look at the architectural blueprint or boxes and arrows, you can see now that this is no longer an integration bus or an ESB. It's a message bus. It's lightweight. Okay, it's just sending messages. It's the idea of the smart endpoints and dumb pipes. Okay, it doesn't always have to be messages. You can also just have synchronous calls as well. Okay, so that's kind of the idea of microservices. Very short. This is not the end of the presentation, but it gives you an idea of where we come from, what we've tried to do with architecture, with kind of trying to balance governance and velocity. And we are now at high velocity, where we kind of have to look at, okay, how do we govern all this stuff? So if you put these big architectures on a scale between governance and velocity, I think you'd agree that mainframes are on the far left. They are very monolithic structures. They're not very fast. The rate of change is very low. Integration buses give you quite some governance, give you already a little bit more velocity because you can split your monolith in different services, and you can have some speed on those, but you're still subject to the integration bus speed for delivering. But microservices give you full speed. Okay, microservices is all about faster time to market and lowering the complexity of this one big mainframe, this one big monolithic structure. Okay, obviously there's still a lot of complexity in other areas, but for development of your business logic, this is supposed to be easier. Okay? So, present day, 2017. Okay? What do we see mostly in our current enterprises? If we don't talk about microservices yet. We see traditional SOA. Okay, it's still there a lot. And we see monoliths. And who's working on monoliths? Right, it's like 50%, the other 50%. Okay, traditional SOA, we've talked about this. The pro is obviously governance. You get great view of what's happening, what's going on in your system. You have strong contract checks. It's easy to monitor and alert on this because you just have this ESB where everything goes through. So kind of seeing what's going on is easy. It's easy to outsource, right? So big companies like this, especially the big consultancy companies. They love traditional SOA because you just have to define a contract and you can just tell some Asian company or Asian team to just execute the work. And as long as you validate with the contract, you're fine. Okay? So this might take a while to accomplish, but eventually just have you kind of have the results already up front defined. So not much can go wrong there, unless you kind of look into the code, but you don't want to do that. So it's easy to work with the Asian companies or Eastern Europe companies. I don't know. Great for slow-paced development. So if you have business requirements that don't need to go fast to market, this might be the best approach. Okay, because you have that governance. You are certain that your architecture is under control. Okay, so this is not necessarily a bad style if you're in this specific situation. Okay, what's bad about this? Kind of a lot. It's a single point of contention. We've talked about this. It's also a single point of failure. If your ESB crashes, everything stops working. The ESB is like a conductor in front of an orchestra. He kind of tells everyone what to do. Okay, and if the conductor falls over or dies or whatever, then it's finished, right? The orchestra is not going to play on itself. Okay, with a microservices architecture, which I'll talk about later, we'll see that it's more like in choreography, where the choreographer kind of tells the dancers what to do up front, and they kind of just do their thing. And if a dancer falls over, then everyone else just continues, and this dancer kind of gets back up, and everything's fine. Okay, so that's kind of the difference on that level. Expensive licenses, yeah, ESBs aren't cheap, and I think companies like IBM and Oracle, they know, and they love that. But for our companies, that's kind of a downside. Heavy versioning burden, so because you have this strong coupling of the contract, you always have to version for every little thing. Okay, I'll talk about that later as well. Heavy shared data model. Okay, so because you also share databases, you kind of have that complexity in all your services. Okay, so you can't really focus on your specific field of knowledge. You have to kind of care about everything. Limiting innovation. It's hard to replace technology in this architecture. Heavy coupling, obviously. Long lead times. High complexity. All this stuff is kind of coupled together. Like if you have high coupling and you have a shared data model, then it's kind of complex to work in, and it takes a long time. Distribution, you're going to distribute your architecture over multiple services. A monolith has no distribution, so that's easier. You don't have to worry about all the fallacies of distributed computing. And it's bad for fast-paced development, right? So this is traditional SOA. So who likes traditional SOA? All right. We'll also again at the end of the session, who likes microservices, who likes monoliths, and which one you guys prefer at the end. Okay, so monolithic applications. No distribution. It's a good thing. You don't want to worry about all this network stuff. If you look at the OZ model, there's a lot of stuff that can go down, actually, or can go wrong, because you have to worry about all these complexity levels. Okay, if you have monolithic application, just worry about the application level. Okay, level 7, easy. Easy monitoring and alerting for a monolithic application here as well, because you just have one big chunk, and this chunk is up or it's down. Alert, true or false. Okay, easy. Doesn't get more easier than this. Believe me, if you work with microservices, this is kind of a nightmare. Quick to get going. Okay, if you kind of have to build something new, and you have a small set of small set of functionality, just do it in a monolith. You know, don't start splitting it up in very, very little pieces and start adding complexity. This is going to just give you a lot of pain, while you can just put it together and be done with it. Okay, so really quick to get going. But there's some downsides as well here. Hard to scale separate components. So let's say you have a monolith, which is serving like an e-commerce website, and like the product catalog, that might be viewed a lot, right? A lot of people might be interested in this, but the payment part depends on how many, what your turnover rate is. But that's probably gonna have a lot less views or traffic than just watching the catalog. Okay, so you might wanna scale this independently from each other. Okay, so a monolithic application doesn't allow you to do this. It's just one. It's like it's atomic. So you have one instance of everything, and you have a second instance of everything. Okay, so with traditional SOA, it was easier to do. And you have the butterfly effect, which I'll talk about later as well. I'll let you figure this out yourself for now. The heavy shared data model. Okay, so everything's together. It's tight, so it's difficult to understand, to comprehend this stuff. It's also limiting innovation. If you want to introduce a new framework, maybe a new language, you have to rewrite everything, right? That's kind of difficult. And heavy coupling, obviously, due to the heavy shared data model as well. Long lead times, same as traditional SOA, and high complexity. Okay, so this is the kind of situation where we are in now, 2017, while we are ignoring microservices. Okay, so being in one of these two architectures doesn't necessarily mean it's a bad choice of architecture. You have pros in each of these sides. But let's see what microservices can do for you. Maybe that's the best fit, okay? So let's go back to monolithic applications, right? Because that's probably what you guys are most using, because I saw like 50% monolithic, 50% microservices. Not that many traditional SOA anymore, but monolithic applications are like the most common architecture out there right now, I think. So what does that look like? This, really easy, right? You have 3-tiered application, most often, where you have a database and you have the shared domain model. Okay, so you have a web layer, which serves either APIs, which would be nice, or pages, web pages or whatever. You have a business logic layer, and you have a data access layer. Data access layer talks to the database. Okay, so that's kind of the most common thing out there, right? Right? Yeah, great. Active people here. All right, so the camera's not following, but that's okay. Cameraman, follow. Okay, so what's wrong about this architecture? Oh, well, what's kind of difficult? We talked about this. You've got a lot of dependencies between the classes. This is an actual case. It's not just some crazy drawing I did in Paint or something. Okay, so as you can see, classes can call other classes, and they can get intertwined. Okay, you can have circular dependencies. You can have all this stuff, which is pretty difficult to understand. Okay, so this is just a dependency graph of a monolith. Gets difficult, right? Now, I talked about the butterfly effect. Who has seen this movie? All right, some people haven't. Go see the movie. It's a great movie. It's about the idea of a butterfly flapping its wings in one side of the world and an hurricane, Jesus Christ, a hurricane happening on the other side of the world due to the, due to the wind. And that's kind of what we can do in our application as well. We can have the same butterfly effect. If we change something in our shared domain model, this gets kind of difficult to refactor. I mean, your IDE might help you a lot, but you might still get runtime issues, okay? And that's something which is difficult to keep under control when you have a big monolithic structure. Okay, so the butterfly effect kicks in. And if you have a lot of classes, okay, a shared domain model, this is really difficult, okay, because you have to understand everything everywhere. Okay, yeah. If you have to think about, let's say you're making an online payment transactional system, you have to understand every little detail of the financial world everywhere in your application. Even though you might be just dealing with maybe what could it be? Maybe just the marketing part of that application. Who knows? Or the blog. You know, if that's in the same monolithic application, you have to care about all stuff because you're dragging all this model in. Okay, so if you just need from this model, maybe just this little part here, that's fine, but you're going to get all this stuff linked to it as a dependency. Okay, so if you do a refactor here, you might also get a breaking change here, or in some business layer where this is maybe used, who knows. Okay, so that's very, very tough. It gets a lot of complexity in your code where it actually doesn't need to be. Okay, so how can we kind of make this easier? Does everyone have an idea? What could be a solution for this complexity? Anyone? Anyone knows DDD? DDD. Yeah, all right, 4 people. And what could be used from DDD to kind of link this together? Right, bounded context. Great answer. So let's first look at DDD, right? What's DDD? Eric Evans, one of the main characters of DDD. Domain-driven design, tackling complexity by abstracting the business domain concepts and logic into a domain model and using this as a base for software development. And he kind of says that, okay, look also, I use this banking idea. It's kind of, in order to create good software, you have to know what software is all about. You cannot create a banking software system unless you have a good understanding of what banking is all about. It's the same thing I just talked about before. One must understand the domain of banking, okay? So you kind of have to understand all this stuff. And then what you can do with this in domain-driven design is go towards bounded context, which is also a term from DDD. Domain-driven design deals with large, complex models, right, like the banking system, by dividing them into different functionally bounded subdomains, okay? Functional composition and decomposition, sorry, and the explicitly defined interrelationship between these subdomains. Those are bounded contexts. Okay, so that's a nice definition, but what do we do with this? And how do we apply this to our shared domain model? We can do this with a couple of methodologies or approaches, and one of them is event storming. Event storming, written by Alberto Brandolini, is a great book that kind of talks about this technique of visualizing events in your architecture or in your system, and kind of trying to structure it. And from these events and the structure that it brings, you could come to bounded context. So here you see an example of something that we did at one of our clients. The idea is that you would sit together in a room with people who know and people who can ask critical questions who don't know, right? So functional analysts who know the system and the complexities, will have a great idea of what's going on in the system, the events that are transmitted in the system, and people like architects or technical leads, they can ask critical questions about things that make the functional analyst think about something they might not think about up front. Okay, so the idea is that anything that goes on in your system, any event, like for instance, a user created or booking registered or something like that, anything which happens, you kind of write on a little post-it, right, on an event post-it, and you kind of put it on here, like this. Anything that goes on, right, you just put it on the sheet. From there on, you kind of chronologically order this. So if you do this, you can see that there are kind of dependencies between these events. Like for instance, if I can read this, yeah. So here, for instance, you have order is sent, and from there on, the hold on, what's that called? The order is processed, right? So an order is sent towards the processor, and he kind of processes it. Kind of simple, but still, it kind of gives you an idea of what's going on in your system. From there on, you kind of add commands. What are things that trigger these events? If you, for instance, have user created, the command is create user. Simple, right? But it's also important to keep these to kind of show what commands can trigger events to get a full sense of what's going on. And from there on, you can get kind of these aggregate roots. Aggregate roots are terms that kind of encompass certain complexity or certain other terms together under one umbrella, for instance. And then you kind of get the idea of, okay, this is talking about pre-planning, this is talking about booking requests, this is about planning, so booking of actual machines, oh, whoops, in this case. Then ordering an asset and an invoice. There are more stuff under here, but I didn't get it on the picture. So all these different aggregates kind of give you an idea of the main topics of your architecture, of your system, right? And from there on, you can see kind of contexts that are emerging from this that have ins and outs, events that are coming in and events that are going out. Okay, so this is kind of the idea of event storming. Now, how do we translate this to bounded context? But the question is it the same as with BPM, where your process is kind of emerging? Not sure. I'm not sure. I know that there's something in Six Sigma, which is CPOX, which is kind of giving this as well. But I don't know about what BPM could give that. I don't know. Maybe. So if you have these terms and you have these contexts where you get ins and outs, you can go towards bounded contexts by using the ubiquitous languages from bounded context. Ubiquitous language is kind of does everyone understand ubiquitous language? Right? Right. So you don't have terms that have two meanings. Right? And you can actually see here that sometimes terms are kind of they kind of do have duplicate meanings, right? And I always use the example of home as a term. Home, what does it mean? Home, where you live, right? Simple. So in the context of your profile, for instance, this has only one single meaning. But if I'm talking about sports, home could be the home base in baseball, right? You run home, you do a home run, right? That's a completely different meaning. You don't want to have this term messed up with the other term, because that gives you the complexity which you don't want to worry about. You don't want to specify this specific difference, okay? If I'm talking about appliances, then home could mean a button on the keyboard, right? It's nothing to do where you live or sports. But you don't want to have this together. Like for instance, an e-commerce website, you could have a profile where you can have a delivery address called home, and you could be maybe selling home. Well, you maybe could be selling appliances like keyboards, and then home might come up. If you kind of mingle this together, right, which is kind of far-fetched, but still, like this kind of this kind of problem you don't want to have in your code. Okay, this gives you the ubiquitous languages, and this kind of emerges from this as well. Okay, so what you could also do aside from this is do static code analysis, like this. So let's say you have you're using Git, maybe, right? Then you can use a tool which I visualized here, which actually goes through your code or through your Git history, and for each commit it looks at which files you have changed. If you've changed files in one module and files in another module, that indicates, well, at the same commit time, that indicates that these have temporal coupling. They are coupled by your commit, right, by changing them at the same time. And that kind of could mean that if you do this a lot, and this could emerge from this analysis, that they kind of should be together in the same module, right? That these modules shouldn't be apart. Okay, so this gives you great information about if you have a monolith where you could do this, then you could see like, okay, these things should actually be together. Okay. All right, so these are techniques for coming to these bounded contexts. But having these ubiquitous languages is very important. Having these bounded contexts is important because then you can focus and you can just put complexity in your area of the code base without having to worry about all the other stuff. Okay? So if you go back to our monolith, the problems we saw here was heavy coupling, spaghetti code. Remember the spaghetti slide? Butterfly effect, and a shared domain model. So what can we do here? What could we do is create packages, right? Packages where you have your bounded context structured. And here you can see that I have, for each package, its own domain model. Right? And you could make this layer, this layer, this layer, just all package protected, package friendly, and not expose them to the other packages. This is super easy to do. And your model and just an interface or a facade gets exposed to the rest. Okay? This is just kind of basic stuff. Right? This is using Java or C# or whatever language, object-oriented language you want to use. And this kind of gives you encapsulation. Okay? And it's important to keep your complexity isolated for each component. You can do this already with your monolith right now. And it will make an improvement. Okay? So using Java packages, you can make sure that people can't access your data access layer from, let's say, like this one here cannot be accessed by this component. Right? So that gives you an advantage here. But there is one problem with this. Does anyone know? Like, it looks good, but is it really enforced? It's not really enforced, right? I can still use reflection, right? But then again, you can write a test which checks the imports. But that's kind of after the fact. So no enforced encapsulation is a problem here. And I think Yannick will agree that there's a better approach to do this, right? Which is? Yes, Java 9, Java modules. It's been released recently. If you use Java, I don't know if in C# you have something like this, but this allows you to encapsulate your code explicitly, enforced. Okay, you can't use reflection if it's not on the class path or the module path. Okay, can't do that. So this kind of gives you a great tool already to kind of go towards a more structured code base with less spaghetti code, less complexity, while still just using Java inside your monolith. Okay, so this is a great way to do this. Okay, I would definitely advise you as a first step. Okay, you might just go to the next level if you're ready for that. So Java modules. What's the problem with Java modules here? What could go wrong? Right? If you do this, well, by the way, Java modules kind of supports hot reloading. So, well, you have to enable it explicitly, but still, if you want to switch out this component with a code change, you can do that while everything else is running. It's great, right? I think you have to use service locators for that. But this kind of gives you runtime coupling. as well. So what happens if my monolith, which is running on this server, an application server probably, what if that server goes down? Your entire application goes down. Do you really want that? Maybe that's fair. Maybe that's a good trade-off. But still, it's a problem if you want to be very resilient. Okay, if you want to do separate scale-out, that's still pretty difficult here. Okay, because you're working in one container, your application server. Okay. So, what could we do to resolve this? Get rid of the container, right? And this kind of implies that you're getting rid of your monolith. Okay, so before you had the modular monolith, and now you have microservices, right? Or at least services, separated and different and separately deployed. This allows you to do easy scale up and scale down of separate components. This allows you to be resilient because if one component goes down, the other ones could still continue working unless they kind of need each other. But if they all call the same database and the database keeps running, you don't even need to talk to the other modules. You don't need to call them, right? You still have the database, right? So this is a great way to decouple. But you're kind of still coupled to the database itself, obviously. Okay, and you kind of have that complexity of the database and the coupling which it brings in all your services. Okay, so data coupling is not so good, obviously. So what could we do? We could split it in separate schemas. Okay, we could kind of use our bounded contexts here, also in the database. We could kind of group the data together in separate schemas and make sure we don't have any foreign keys or primary keys or any foreign keys linking to another table of another service. Okay, so this kind of splits the bounded context all the way through. Okay, so this is difficult. I'll talk about this just in a second. Why? What you could also do from there is just put it in separate databases, because if your database goes down, everything stops working. Just like if your monolith went down, everything would stop working. Okay, so here you can go to the next step as well, and you can actually get it in separate databases. Okay, so now we don't have any communications anymore, right? That was the problem. We had the database before where we could just communicate, but now we don't have anything. We don't have the container of the monolith anymore, where we could kind of call binary. I mean, you could call the functions of other services. Now we don't have that anymore, and we don't have the database as a means of communicating anymore. Right? So how could we communicate? We could do it with SOAP. Right? Who's in favor? All right. 2 enthusiastic SOAP lovers. 3. Okay. Yeah, but we talked about SOAP, right? SOAP has a downside as well. SOAP is full contract coupling. Well, I suppose you could kind of have tolerant reader principle there as well, but it's much more difficult to do, and it's not common practice at all. Right? Common practice is to generate this client library and get full coupling in each service. So let's say you just need one field from this entire payload. Right? You just need that one field, right? And the producer knows this. The producer knows I only have one consumer, and he only has that field. He only uses that field. But I still have this entire payload. And nobody else uses all the other fields, right? Let's say that's something that could happen. Maybe the other fields were used by another service, but that one was removed afterwards. Now you have to change something in one of the other fields, and this consumer is not even using it. You still have to add a new version. Why? There's no need. Nobody's using it. And you can just, it should be forward compatible, but it's not, because you have this coupling, this early binding, you could call it. With SOAP, you always have this, okay? And you have the full model from the producer always imported in your consumer. So is that really giving you bounded contexts where you only have to focus on your piece of code? Maybe, maybe not. It's kind of difficult to say, because you have this library pulled in. And the versioning is heavy as well, obviously. So we could do REST, right? REST is more lean, okay? It's maybe a lot less, has maybe a lot less, like maybe it's not as supported in the enterprise as much, but still, it's most. I mean, currently it's probably the most used style of communicating, especially because the World Wide Web is built on it. Right, REST level 3, by the way. Just cool. But this REST style kind of also gives you some problems. If you communicate with REST everywhere, you kind of you could do it with asynchronous fire and forget. So you just launch, let's say, you do a post to some like post of the customer, and you add a payload, and you don't care about the response. The producer, no, the reader of it and the consumer of this post, the server, sorry, they could just say accepted, right? And the sender wouldn't actually know what happened with this consumer, right? This would be an asynchronous way of communicating. You don't care about the response. You're not waiting. You're not blocking. Okay? But mostly this is used for some other purpose. It's just you send something, like you send a request, like get me all the books of a store, and I'll wait until you send me everything. Okay, that's coupling, because it's kind of introducing latency. It's temporal coupling, because you have to wait for the other service to respond. Okay, so you have to block. And if you kind of have a lot of requests that are being sent to this guy, and he has to wait a long time on this guy, right? Then he has threads piling up. Okay, you could work reactive, of course, but mostly if you don't, threads are piling up, and you only have a limited size, limited thread pool, which kind of it kind of has a burden on this service as well. Okay, so this might not be the best style. You could work around this with circuit breakers, but still you have this coupling, the temporal coupling, and latency is always there. Then you have consumer-producer coupling, of course, because this guy knows about this guy. He kind of has to do a handshake up front, right? He has to know, I'm calling service B, I'm service A, and service B knows I'm connecting to service A for a response. Okay, so they both know each other. And that's probably in the code, hard-coded. Okay, so that kind of communication is maybe not optimal if you want to scale this out. So what could we do? Integration bus, right? ESB. Nah, let's not do that. Single point of contention, single point failure. We talked about this. Let's do a lightweight message bus. Okay, we have a lot of them, right? Like Rabbit, like ActiveMQ, like MQ series, maybe, or which ones we also Kafka, for instance. It's a great example of a lightweight message bus. The difference here is you don't put any transformation logic in here. This is just sending events or messages back and forth, right? It's not doing any transformations, and this allows you to keep business logic in here and not in here. And you don't need some bottleneck team here managing what's going on in the bus. Okay. So this is a great way of communicating, but having only this style kind of gives you implicit coupling. So you might think, well, now we don't do a handshake anymore, so service A doesn't know it's sending to service B. Great, okay, we are decoupled, and decoupling is always good, but in this way, we still have coupling. We have implicit coupling, not explicit anymore, and that's maybe even worse, because you don't see it, because this service A is sending its events to service B, and service B reads these events. If service A changes these events, service B is going to fail. That's still coupling, right? So don't be naive in this way of working, where you might think that this is the best way of doing things because you don't know of producers and consumers. You still have to know about them. So mostly you'll have a mix of REST and, well, synchronous and asynchronous communication. Okay? So, but this, we still have the sense of eventual consistency. Okay, who knows about eventual consistency or heard about it? All right, half. Eventual consistency talks about data. We now have data here. We used to have our big data structure here, and now we split it up in pieces. And these pieces now have to sync. Before we had ACID transactions, right? We had consistent transactions that were dealing with maybe multiple tables, but you could be sure that if you did an insert and you read and you read the result of that, that you always had consistent data, right? With this, it gets worse because you're now not talking to one database anymore. You're not talking to, from one client, you're not talking to the databases of the different services. You're talking to their interfaces. Interfaces could also be events, by the way. Okay, so eventual consistency is something we have to look at. This, by the way, is all microservices, right? Just in case you didn't. All right, so shared data. Okay, so let's get a principle straight here. Okay, with microservices and with shared data, which it mostly gets, I mean, you're always going to have shared data until you, unless you didn't split your database yet and you communicate over the database. But in most cases, you won't do that. You will have something like this. You will have always an owner and a system of record. One service with its database, which owns the data in that database. It's the single owner of that database, of that data inside the database. Okay? And the other one, the interested party, the other service, it has read-only and non-authoritative cache. Okay? It's important. It does not update that data itself. So it doesn't do some changes in the data. Well, if it does a cache here, let's say it's interested in this data. This could be customer data. And I'm interested in customer data, right? What I could do is I could just pull a cache. I could just ask, give me all the customers. Okay, here are all the customers, thanks. I put it here in a separate table. I update these customers because I have certain functionality here in my bounded context, which also deals with customers, but in another sense, in another way, right? But still, I want to update this customer. I don't kind of do a synchronization with this system like right away. I don't do that. I only have a read-only cache, and I'm not the author of that cache. Very important principle to get right. Okay, because you can kind of mess this up really quickly. Okay, so if you get this as a principle, then we can talk about how we can deal with shared data. Okay, so we have three approaches. One approach is synchronous lookup, which is super simple. Service A synchronously calls service B to get information. And service B gets this from its database. This is super easy, right? This is also a good way of doing it, but it's maybe not as scalable. Approach 2 is asynchronous events. So let's say I'm service A and I'm dealing with consumer data, or customer data, sorry, customer data. Then I can emit an event that my customer data has been created or updated or deleted. And anyone who cares about this, which could be service B, receives this event and kind of stashes it locally in a cache, right? It doesn't change that. It's just the cache is there, and it might be outdated with the system of record, but it's still a version of that information. Okay, that's just local lookup, because then service B can, if it needs to get some information of the customers, can just look in its cache, see the latest version that it has, and use that to deal with any logic that it wants to do. Approach 3 is shared metadata library. I don't think this is very much appropriate here right now, but still you could do this. We're talking about server-oriented architecture, service-oriented architecture. We don't always have to work with services. We could also have a library which has some immutable constants or whatever. If you're talking about countries in the world, you could just put this in a constant and then put that in a library or something. Okay, this might change once in a while, but I mean, it's not worth putting in a separate service which exposes the countries in the world, right? This is still a way of sharing data. Okay, so mostly you're gonna have approach 1 or approach 2. So now if you wanna have joins of service A's data and service B's data, what we could do is we could join this in a client application. So a client application could call service A, retrieve data, call service B, retrieve data, join it, ready. Right? This kind of happens all the time. I think every web application in the whole world which uses multiple databases uses this. And it's very straightforward. Approach 2 is a little bit different. It's materializing the view. Okay, so you can have a cache which is comprised, or it's kind of the combination of events emitted from service A and service B. Okay, so it combines it in a joint view. It's kind of the same thing as in databases. It's very common, right? Where you have a view where you join this information. This is also eventual consistency because you just use events to update it. Okay, and this is very similar to CQRS and event sourcing, which I'll explain in a bit. But it's kind of giving you a view of the data which you want to use, like your specific query is structured in this view, and writing it is done in separate services. So your reading is separate from your writing. Okay, so kind of CQRS, right? But I'll get to that. And what about transactions? Right, this is the difficult part. With transactions, we can work with Sagas. Okay, you could use distributed transactions. You could XA transactions, right? But this kind of gets you in a very difficult position. It's kind of a road with no end. Like for instance, if you have a queue and you have a database and you're writing something, for instance, the user is created. I have to write that to my database. I have to write my user to my database. But I also have to emit an event to the entire system that my user is created. If I do this in an XA transaction, if something would fail in the queue, I would have to roll back the database. If something would go wrong in the database, I'd have to roll back the queue, which is impossible, right? So I would always have to put the queue last. But still, this kind of gives you a rollback mechanism, which could fail on its own. And what if that fails? You know, that's kind of a road you don't want to take. And it also is not scalable. Right, this is a performance hit. It's also working with logs, so that's kind of not very concurrent. So the Sagas are here an answer to this. Sagas are kind of defining a workflow between services that are part of a transaction. So if you have service A, B, C, you'd have a Saga, which spans all these services. Service A produces an event. My customer information has updated, and it updates the database in an ACID way. So the ACID transaction is there in that context of that service, which is great. Then service B kind of deals with orders. So I'm using this customer event. Great. And can now put an order, an onboarding order for a customer or something. I don't know. ACID transaction in the database. Great. Okay. Everything's working fine. And then from there on, my order process has started. So now I have to do a delivery. So in my delivery service, I can now also write something to my database. A delivery has to be started. Okay, so now I have 3 separate ACID transactions that happened. But what if there's something wrong? What if some of these ACID transactions failed? Right, then you can have a rollback mechanism. And each service has to provide its own compensating operation in reverse. Okay, so it has to provide a rollback for what it just did. And that works with events. So if there's an event sent from the third service that something went wrong in that service, then the second service can do the rollback, and the first service can then also receive that event. But the requirement here is that you need to have at least once delivery of your events. You can have 2 styles here. You can have at least once or at most once. Okay, we want the at least once delivery. You can't have exactly once. That's impossible. That's a fallacy of distributed computing. And your consumers have to be idempotent, right? So if you receive this event twice to roll back, your consumer of that event must act exactly the same way as the first time, and it must be idempotent. You should have the same result. Okay, that's the idea here. Okay, so this is a way of doing transactions in a distributed fashion without having to rely on distributed transactions. All right. If this is not entirely clear, yeah, we'll talk about this later as well. So, I talked about CQRS and event sourcing. I got a couple of slides just to kind of shed a light on this, but I think CQRS kind of familiar. Who knows CQRS? All right, so it's separating the view from the right, the read from the right, and mostly in most applications you have CRUD, which is your create, read, update, delete. which is the same for writing and reading. Okay, you just have the same model. But here, you can have a read model and a write model. A write model optimized for writing data, and a read model optimized for reading data. This can mean a huge improvement in performance, right? Because you don't have to deal with one model which is not optimized for either side. Okay, so you can have this in one database and just have two separate models in your application, but you can also have two separate databases. And here you have the possibility of having a cache or some kind of a materialized view as a read side, right? So the read side might be just a view optimized for reading, and the write side could be something where you just write information to. Okay, so let's say you have customer data, and you have a whole bunch of information which you have to store, right? That could be here, but when you read it, you have to kind of do joins, or you have to just get a little piece out of this data, right? Then it might be useful to asynchronously kind of build up this materialized view, and read that instead of doing these expensive joins or queries on the right side. Okay, this is kind of CQRS. You can apply this also in your database, in your microservice architecture. But where it really gets interesting here is with event sourcing. We talked about having a user created, that being put into a database, and an event that had to be sent, right? Two different operations that can go wrong. What if we use the event as the database as well? We don't have to have two separate processes aligned. This could be cool, right? If we could do that. Welcome to event sourcing. All right, event sourcing keeps, in the right side, a store of events. So all the events that you're emitting, for instance, user created, user updated, user processed or whatever, user deleted, you could just write all this stuff right in here in the event store, okay? And then when you need to read this stuff, you could just replay all these events. Okay, if you want to know what's the current state of the user, just replay it. It's pretty straightforward. But you could do that, but still, I mean, if you have like a bank account and you have 10,000 transactions, credits, debits, debits, you know, all this kind of stuff together, and you want to see what's just my balance. I don't see my balance. I just have add, remove on my bank account. Then you have to start counting everything. You have to go through all these different events. It could be a lot of them, could be 10,000 of them, to just see your balance. If you go to your bank account website and you check your bank account and you have to wait 10 minutes before you see your balance, you'd not be very pleased, right? So what can we do? We can take a snapshot. Right? After a certain amount of events, we can say, okay, right here, we're going to take a snapshot. We're going to count all the credits and the debits together, and we're going to insert one credit or one debit, right? Which is then a collection of all this complexity together in just one event, right? And this one event can then be used to read, right? Because you just have to count maybe 10 events. Or you can just have a materialized view, which is a normalized view of the denormalized events, which you read from. This is also CQRS. Okay, you read from snapshots or from a normalized view, and you write in a denormalized event way, or the other way around, whatever. Okay, so this is a way of kind of having an event store as a source of truth for your data. Okay, so I talked a lot about data right now, but that's the most difficult part of microservices. Your eventual consistency. Okay, you're gonna have to deal with a lot of these things if you start splitting your data in separate tables, separate schemas, or separate databases. So you see, this is not that straightforward. Okay, so let's go back to our microservices. We were here, right? So one more thing here, which might not be that easy. If we now have all these services here, see 1, 2, 3, 4, 5, you can have a lot more. You have a lot of databases here. These things could go up or down. You have to deploy them through a very automated deployment chain, continuous deployment, hopefully. So this kind of gives you a lot of complexity to deal with. So what could be the answer here? Anyone has an idea? To deal with all these services that could go up or down at any moment. Anyone? Platforms? Yeah, exactly. The platform should take care of this. So you have high operational complexity. You can build a platform around this. Like, for instance, Kubernetes, right? Potentially Kubernetes. Or others. There are a lot of them, right? As you can see, they range from infrastructure as a service all the way to application platform as a service, right? A couple that you might know are Cloud Foundry, OpenShift. Of course, the big cloud vendors: Amazon, Google, Azure, maybe Oracle, maybe SAP, maybe not so much, but they are out there. And you have different ways of abstracting things. And for instance, with Amazon Web Services, it's basically just infrastructure as a service. Microsoft Azure as well, or Azure, but they also offer some other services like container services and that sort of thing. Same goes for Amazon Web Services, but they call it Elastic Beanstalk. Oracle Cloud also probably has something for this. And SAP also has something for this. They have Cloud Foundry. Right? Cloud Foundry is an application platform as a service. But between these two, like application platform as a service and infrastructure as a service, you also still have the container platform as a service, or container as a service, or whatever you want to call it. And those are the Kubernetes. Kubernetes or OpenShift, which builds on top of Kubernetes. You also have DCOS, Mesos, or Swarm, for instance. They are orchestrators for containers. And if your services are building containers, then this is a great way of dealing with that complexity, because it kind of gives you a certainty that if your container goes down, it will spin up a new one. Cool, right? And Cloud Foundry, OpenShift, and obviously the distributions from Cloud Foundry, they offer you also something called source to image, which kind of bakes a application. So if you're using Java, then Spring Boot kind of gives you a jar file. You can just say, this jar file, put it in the cloud for me. I don't care how, okay? And it's gonna wrap it in an image, a build spec of the platform. The platform is gonna take care of updates and of patches of the underlying distro, or Linux distro, or yeah, Linux distro, and it's gonna run that for you, okay? And it's gonna provide you backing services to integrate with really easily. So these are the different kind of platforms you can use to deal with the operational complexity of your deployments and of the containers that are running, or the applications that are running as microservices in your architecture. Okay, so now we have a platform. Great. But we still have complexity here. The complexity lies in here, right? Communication. Communication is difficult. It's hard to, it's over the network. And as we all know, network can fail, right? Network always fails. The fallacies of distributed computing, I've talked about them. The network is always fast. No, it's not, right? There's no partitioning. Yes, there is. There's always something wrong with your network, okay? Or at least there always will be something wrong with your network. Dealing with this complexity, I've talked about circuit breakers before. That's something you have to deal with. And you can deal with that in your microservices, add the library, you know. I'll talk about that later. But that's kind of difficult. So what we could look at is high technical complexity for communication. How we can solve this is service meshes. So I suppose nobody has heard about service meshes, right? Whoa, this one guy. Okay, so for you this will be very easy. A couple of examples here are Istio, Linkerd, or OpenContrail. So these things kind of try to help you with dealing with this communication complexity. Okay, the network that's between your services. Okay, how does this work? I've kind of took the liberty of lending some images from a blog site because I was too lazy to make them myself. But I will explain them with these images. So, service A is communicating to service B. Still following, right? Cool. Service A is on computer A. There's a network stack in between to computer B. Okay, still simple. Now you have business logic and flow control in each of these services. Okay, so what do we have to do here? We have to kind of focus on the business logic in our service. That's what we really want to do. We don't want to care about the flow of our network, how packets are being sent back and forth. We don't want to care about that complexity. Okay, so push them down to the platform. Okay, so into the networking stack. So we don't have to care about business logic. Okay, so when we want to do these calls, we will eventually fail. And I talked about requests piling up in a calling service because the producing service is slow, right? And eventually your calling service will go down because of too many requests, right? We can deal with this with circuit breakers. Okay, so circuit breakers allow you to protect your service and the producing service from overloading by just kind of the same way your circuit breaker at home works. Okay, if you have a lot of calls going through your network, or let's say there's something wrong with your laundry machine, right? there's some kind of short circuit there, right? Then you want your circuit breaker to explode, otherwise your whole house will burn down. Same thing here. If something explode, if something goes wrong in one service, then you want to make sure that your other services aren't dependent on it anymore and are just failing fast. That's a circuit breaker. Okay, so you gotta build these circuit breakers in your service, right? You gotta put that complexity in there. But this is really just network stuff, right? You don't want to be dealing with this stuff in your service. This is difficult. You have to fine tune it as well. And you also have to find the other service. And we could just hard code the IP. But if the IP changes, we're gonna use DNS maybe. Okay, but what if your service is down? Wait, you still have the time to live on DNS. Okay, maybe you will use service discovery. Okay, so that pattern kind of is familiar to most of you, I suppose. You're going to discover the service by calling another service which tells you where the service is located. And everybody's sending heartbeats to this discovery service, the service registry, to say, I'm still here, right? So the service discovery has to be integrated in each service. This is also some complexity I don't want to deal with. Okay, so what can we do here? We can put this stuff in library, and Spring Cloud does a great job of this if you're using Spring. Okay, it gives you some libraries, but really, it's still part of my application. So maybe I could just get this out there, get it out of my application. I could do this, and we could put it in a sidecar. Right? Like Netflix OSS kind of supports this out of the box. But if you have a sidecar, it doesn't have to be, it's not even part of our application anymore. We don't really care what the sidecar is built with and who and how is it working. It's outside of our application, right? And it's just like a proxy which is running next to it. So what could we do is we could kind of use all these sidecars next to our services, and we could create a mesh from this. Right? You know what I'm getting at? Service mesh. Yes, this is it. So the service mesh is kind of a bunch of proxies that are dealing with this complexity of circuit breakers and service discovery. And it's kind of connecting this to a sort of control plane, which allows you to kind of have insights, monitoring, alerting, and kind of deal with this stuff separately. Part of the platform. Just like you have a platform as a service, which deals with the complexity of your deployments and operational complexity. Okay, so now we have communication in the platform, which is great, right? Unless you're starting to build an ESB, of course. But that's maybe not the best choice. Okay, so as you can see here, we will push down the complexities of the network level in the OZ model. We will push it down out of our application layer. Okay? That's the idea of a service mesh. And eventually we'll get something like this. Okay? So this is a great way of doing it. And I've stole all these pictures from this blog post. So if you want to read all the information behind it and much more, I've just given you a short overview, then please go have a look. Okay? I'll send the slides afterwards. So back to our architectural boxes and arrows. Okay, so we're almost there. A couple more slides. But we could still do something more here. Okay, so we are actually moving further into decoupling everything, and we're moving towards, well, you still have high complexity for deployments, right? So your deployments are still difficult, but we're moving towards something called serverless. Who has heard about serverless? Right, serverless is you don't have any servers anymore, right? You're, well, not really. You still have a bunch of servers. It's actually a server-full platform. It's full of services, servers at least. Why? Because you have all of a sudden removed your microservice, which is just a function, and you can have a bunch of functions, like a lot of functions. And all these functions are obviously running on servers. Okay, you just don't see them anymore. So you have a lot of servers in the serverless platform. But still, how does it work? Instead of having all your different services as Docker images or something like that, now you just have a single service, which has a single function. I'm sorry, which is kind of just a method, which could call other methods inside, but it's one interface or one signature, which consumes events and it emits events. Okay, and it doesn't care about who's reading these events and who's sending you these events. It's just doing something with events, right? It's pretty straightforward. You have to kind of comply to the platform's signature, how the events should, how your signature should look like, what it should look like, and what the events should look like. But then you can do whatever you want inside the function, and you could write it to databases or whatever. Okay, so this is kind of giving you the next level of microservices. This is the Microservices or the nano services, right? Super small, just one method. Okay, and the benefit here is that everything is managed by the platform, aside from your code. You have, well, if you have to upload your code, so it's kind of managed as well. So your code here of your function is uploaded to the platform, and the events that are going out and are coming in, they are just managed by the platform. You don't have to have a message broker anymore. This here, you don't see it anymore. This here is completely software as a service as well. So you just have to deal with your functions. And this gives you a high level of automation, the highest level of automation you could think of. But of course, it's a trade-off as well, because now you're coupled with the platform. Okay. In our quest for decoupling, we've decoupled ourselves so much that we're now coupled to the platform. Okay, so this is the outermost, for now, I don't know what the event lacks, but for now, this is the end station in our road towards autonomy and decoupling. Okay, so we've come from monolithic structures, and we've gradually broken them down into pieces. We've decoupled certain parts. First, we've decoupled the packages, then we've decoupled it into modules. Now we've decoupled the database into separate schemas, and we've taken out the schemas into separate databases, and we started to communicate over these different services. Then we've kind of seen, okay, all these microservices, well, we've pulled out microservices, of course, can't forget that one. It's kind of crucial to microservices. And we kind of ran them on a platform, or on a service mesh on top of a platform, or even as functions on a serverless platform. Okay, so this is our road, and each of them came with trade-offs. Okay, they all have certain pros and certain cons, and it's up to you, everyone here, to kind of see in your specific case how far do you want to go. Okay, because this also doesn't give you the most, the best situation you can have, because you have heavy platform coupling here. Okay, so you have to be fully in the cloud, and you have to be fully locked into this vendor. Unless you use serverless framework, I suppose it's called, which kind of gives you an abstraction of your signatures, but still, I mean, you're really tied into the operational side of the platform. Okay, so this kind of could give you an idea where we can go, and I hope that by moving through the monolith, refactoring towards microservices, you've gotten kind of an idea what microservices are about. So now let's look at the definition of microservices, right? Instead of starting with this in the first slide, I kept it for one of the last slides. The microservice architectural style. Okay, what is it about? It's an approach to developing a single application as a suite of small services. So we're going to split it into small services. Right? They are all running in their own process. Right? So they're not in the same container. That was the difference. We pulled out the container and we had microservices. They are built around business capabilities. So I've talked about event storming, a way to get to business capabilities or bounded contexts. They are independently deployable. So obviously, if they are running in their own process, you should be able to independently deploy them. And they are fully automated in the CI/CD chain. Okay, that's an important part. Full automation, which kind of leads to DevOps. Okay, so I'm sure. I mean, who has heard about DevOps? And now I know who's sleeping here. No, DevOps is kind of a necessity. Sorry, for using microservices. And there's a bare minimum of centralized management for these services. So the ESB is not what we want. Bare minimum, the least you need. Okay, you still need some governance, but you don't need this big ESB structure with a bottleneck team behind it. And these services, they may be written in different programming languages and use different data storage technologies. That's a benefit. So if we look at DevOps in this case, I'll shortly go through three big points in DevOps, which are crucial to working with microservices, to delivering microservices. DevOps is kind of the way that, if you look at the Puppet Lab state of DevOps reports, we see that high-performing DevOps organizations, they're capable of deploying 200 times more frequently, and they have 2,500 times shorter lead times. And when they have a failure, it's 3 times fewer failures, and when they fail, they recover 24 times faster. This is great, right? If you're this kind of company, I mean, competition is kind of lost already, right? You'll disrupt everyone. So how do we do it? DevOps. Who has seen this movie? Great. Which one is it? Right, Dr. Strangelove. Wow, it's a black and white movie. And it's a really awesome movie. It's from the time of the Cold War. And Dr. Strangelove and How I Stopped Worrying and Started to Love the Bomb, which is the full title. There's the idea of the war room, where the President of the United States has all his subordinates giving him advice. And yeah, of course, they don't agree with each other, start fighting. And he has to intervene and say, "Gentlemen, you can't fight in here. This is the war room." Funny, right? You see? Right, can't fight in here. Yup. The idea here behind this slide is, let me clarify. It is actually that sometimes if you have an issue on production, we have a war room. Right? Who's been in a war room? Everyone. Great. So it's kind of a tough situation because manager is breathing down your neck. There's a lot of stress. People are sweating. It stinks. And we kind of have to work together now. All the people from different divisions who can contribute to solving this problem, they all are together, and they don't want to talk to each other because they're used to sitting in their own floor, maybe in their own building, and they have a ticketing system to talk to each other, which is great because they don't have to talk to people face to face. But now they're sitting next to each other, like, what the hell is this? So they're really quite uncomfortable. But it turns out that at the end of the day, stuff gets done. The problem on production gets fixed. Maybe it's because of the manager, has a whip. Maybe it's because people start talking to each other. One of the rules of the Agile Manifesto is that there are people over processes and tools. Right? People interaction is crucial to agility. And this is the same for DevOps. So DevOps kind of puts teamwork together. People together and teamwork first. So people from different divisions, everyone who can put an idea from its inception phase all the way into production needs to sit together in the same team. Because if this works for production issues, Why wouldn't we do this for delivering value to our customers, making money? Right? This is super common sense, right? But this is the most crucial idea behind DevOps. It's not just Dev and Ops, it's everyone who can get a feature in production, put them together, okay? That's the first rule about DevOps, and you need this to build microservices. These bounded contexts is around a certain product, and you have product teams, right? It's the same thing. DevOps teams are the how do you say this? Is the humification, is that a word? Of the architecture microservices. If you don't have one, but you only have the other, Conway is going to get you. Conway's law says that your architecture is always going to be a representation of the communication lines in your company. So if you communicate over a ticketing system and everybody's in their own technical silo, building their own technical layer, it's going to be a technically layered architecture. It's not going to be a functional bounded context-oriented architecture. Even if you try, it's not going to work. Okay, we tried this at some of our clients. Didn't work. Well, yeah, they think it's working, but it's not. So, next pointer of DevOps is this one. Right, who knows this movie? It's a movie, by the way. Sorry. Final Destination, yes, great. Final Destination. So this woman, unfortunate woman, she is my illustration for a specific theoretical study that happened. It's theoretical, where some scientists came together and they kind of thought, what would happen if we would put a spike on people's steering wheel instead of an airbag? Right? Or what would happen if we would put explosives in the bumpers of cars? Would we have more deaths or not in traffic? Turns out, a lot less deaths, because people don't want to die, right? They see the spike right in front of their face, and they kind of drive carefully, right? Duh. But this is kind of relating to software as well, because if people put something in production at the end of the day on a Friday evening, quickly, without testing it, right? It happens, come on, you've all done it, right? No? Maybe. Then at 3 a.m. in the morning when things break, who gets called? If it's that same guy, he's going to think twice the next day, or the next year, or the next, ever, for before he kind of puts something in production. Okay, he's going to think, because he's directly impacted. He has a spike because of his pager, right? The pager is a spike, right? If there's some poor operational guy who gets woken up and he has to fix something with a run book, has to fix something in the night, and then a Monday morning, you come to the office, and this one guy says, dude, really? You messed something up on production? It's like, okay, too bad. I won't do it again. Whatever, right? This is kind of the situation you don't want to have. Maybe putting this guy, this operation guy in your team is already a good step in the right direction for companies that are in a migration. Because then you have to see this guy's face looking angry at you the entire day. And that's already something. So Werner Vogels put this as you build it and you run it. Okay, just because you have to take responsibility. That's an important part of DevOps, take responsibility. And you need to take responsibility if you're going to work with microservices. Because microservices give you a lot of freedom, because your specific service, it's not impacting any other services if you kind of choose to write it in Go or in Kotlin or whatever, right? But you need to be professional about this, right? You need to take responsibility for your choices, okay? So this is an important one. And then the third one I wanted to highlight here for DevOps is this guy. Who knows this guy? Jeff Bezos. We have a Jeff in the audience. So Jeff Bezos, he's the CEO of Amazon, right? The big shot there. And he decided a couple years ago that he wanted to introduce API-centric architecture in the company. So everybody now has to work with APIs. Before, people could just call databases from other teams without problems, and you would get that slide which I showed in the beginning with spaghetti, and everybody calling each other whatever, nobody knows. Dependencies everywhere. So he said, guys, we're gonna do this better, right? We're going to call an API if we want some data. Call the API of another team. And if you want to expose your data, create an API for it, right? We can do this, guys. Let's do this. And then he said at the end of this memo, a little memo to everyone in the company. At the end of the memo, he said, anyone who doesn't do this will be fired. Thank you. Have a nice day, right? Nice guy, right? In Belgium, this probably wouldn't work because it's kind of the unions wouldn't like this. And you'd have a day like today where traffic is insane because everybody's, not working. But still, this is important. Why? Because people are used to being in their comfort zone. They are used to sit behind this ticketing system and just get some work and then just sign off. Right? They don't want to talk to people. They don't want change. If you have people working 40 years in the same way, they're not going to change all of a sudden. Okay, so you need this guy. You need to have this board buy-in. The board needs to say, now we're going to do DevOps. We're going to do microservices, but we need DevOps, cultural change. We're going to go through a digital transformation. This is important. You have to have a digital transformation, the cultural change for microservices. You can't do microservices without the product teams, without the responsibility, and without this guy. Okay, so that's important. And then, of course, DevOps also means automation. Don't want to give the feeling that DevOps is all about culture. It's also about technique. So you have to automate tests, and you have to automate deploys. Everything you have to automate. Okay, so that's an important one as well. And if you get this, then you're going to succeed in microservices. If you can't do any of this stuff, don't do microservices, right? So the why for microservices in this presentation, why would we do microservices? If you don't do this, don't even do it, okay? If you don't focus on automation, it's gonna be very bad. Okay, so microservices, microservice. Right, it's a hype, right? But let's get down to what really matters here, like evaluating the pros and cons. This is the complete the complete trade-off table, whatever. On the left side, strong module boundaries. Now you can work in a bounded context. So you only have to deal with your complexity of your specific ubiquitous language. This is great, right? You have independent deployments. You can go to production whenever you want, not whenever some some release management team says you can do that. Okay, so you have full flexibility to go production. You can do continuous deployment if you want, but maybe you want to stop at continuous delivery. Could be. You have technology diversity. You can choose any tool, any framework, any language you want for each microservice separately. Wait. Disciplined professionalism. It's on the right side. It's a negative, but maybe it should be on the left side. Everybody needs this everywhere anyway, but here it's very important because you can screw so much things up. Okay, by choosing whatever you want, whichever hype you wanted, whichever bandwagon you want to jump on, right? Security segmentation you can kind of define. If you work on a banking system, you can say, like, for instance, in this part, in this microservice, I'm doing transactional logic, so I want to have a lot of security on this one. But my marketing microservice, I don't care, everybody can see this. I don't want to put that burden of that complexity on that microservice as well. It's separated code bases. You can just put that complexity there and not over there, right? Simple. Separate scale out. You can scale one service to 100 instances and the other one to 10,000, right? So different possibilities there. Parallel development, different code bases, separate teams, product teams, so you can work in parallel, right? That's an advantage of a traditional SOA as well, right? Remember that? They could work on this, they could outsource this. This is hard to outsource, by the way. You shouldn't really do it, I think. And then you have sacrificial architecture. This is a term from Martin Fowler. So throughout all the years, we've tried to rebuild our monolith by putting together a tiger team and, well, a team of all the brightest minds in the company, and kind of get together and said, like, now we're going to build it better, right? We're going to build it the right way. We're going to foresee what's coming in the next 10 years. Okay, because last 5 years, we had the wrong setup. We tried to do something, but it wasn't working out. So now we're going to do it the right way. So these Tiger team members, yeah, let's do this. New technologies, new framework. Okay, let's do it. They're going to build this new monolith. And then all of a sudden, you see after 5 years, all the Tiger team members are gone because it's not interesting anymore. And you're kind of left with this one monolithic structure, which was built for functionalities from 5 years ago, which are not aligned anymore with what we now need, what the company needs now. So that's always going to happen. You're always going to have the same kind of pattern coming back. You're always going to have to rebuild that monolith. So sacrificial architecture says, we accept that we can't do this. Okay, we accept that we're going to fail. So let's just kind of deal with this. Let's accept that we can't build something which is going to last for 10 years. So let's build something which can be easily replaced. Okay, let's build something which is sacrificial. We're going to sacrifice our architecture for the next time we're going to try to build it. We're going to build services which are easily replaceable. Loosely coupled services are easy to replace. You can just replace one microservice when you think it's due time, and you can use a new technology while the other ones are still running as before. I mean, that's really easy to do. You have more system resilience, right? You all agree? Maybe not, right? It's on the left side. It's because if you architect for resilience in microservices, you have better resilience than in a monolith. A monolith, if you have a memory leak, will go down altogether. Everything will go down, right? It's not so good, right? But it's better than if you have a microservice architecture and one service is going down or is not coping with the load, that all the other services are that are dependent on the service are kind of seeing, wow, I have to wait so long for this to respond, and they're blocking all the other threads. Just like I talked about before, they're also going to go down. You're gonna have cascading failures, right? If you use circuit breakers, for instance, you can kind of circumvent this. And that's architecting for system resilience. You're going to design for resilience. Okay, if you forget about this, you're going to be worse. It's going to be worse because you're going to have your full system going down and you don't know where the cause is and all this stuff. It's much harder. And with a monolith, you just have to bring back up that one monolith and it's fine. Okay, so this one, normally, if you care about, if you really take care of this, then you'll have better resilience. On the right side, distribution. The first rule of distributing design is don't do distribution because it's much more difficult. Okay, so we saw I kind of talked about the fallacies of distributed computing a lot. This is this point. Okay, things will go down, things will fail, things won't respond, things will be slow, all this stuff. You all have to deal with this stuff. Eventual consistency, we talked about data as well. So your microservices, they are now no longer asset. So you have to work with eventuality. And a lot of times, your use cases are kind of okay with eventual consistency. If I just go to a website and I watch the website after 2 minutes, I read it, I'm eventual consistent. Even just if I just load it and it's presented to me, it could already be different than what's on the server because the transport time is accounted for. So many of the use cases that we deal with are okay to be eventual consistent. Okay, so this shouldn't be such a big deal. Except if you're, for instance, in trading and you have the stock exchange on your screen, that's kind of has to be real time, right? Or other systems that have to be real time, but there are not that many. I talked about disciplined professionalism, operational complexity. You have a lot more things that are out there that can go down that you have to deal with. You have to have monitoring and alerting on all this stuff. You have to have separate continuous deployment pipelines for all this stuff. A lot more difficult. And cultural prerequisites. You have to have DevOps, right? Or at least a migration plan towards it. So these are the pros and cons. I hope this gives you an idea of what the benefits of microservices are and what the disadvantages are. Okay, and you have to really like think hard before you choose this. But if you want velocity, if you want to go fast to market, microservices are guaranteed the best, or function as a service perhaps, but microservices are a very, very good way to increase that speed to market. Okay, your complexity will also go down in your separate microservices. Okay. Then a word of advice from Simon Brown. If you can't build a monolith, what makes you think microservices are the answer? That's a very well-known architect who kind of is in favor of a modular monolith. We talked about this. Java 9 modules are really good with this. And to end our presentation with, Sam Newman. Sam Newman talks about building microservices in his book, and he's kind of the de facto standard if we talk about microservices architects. He's the guy. You know? So he says, if you're coming from a monolithic system point of view, you'll have to get much, much better at handling deployment, testing, and monitoring. So these operational complexities go up to unlock the benefits you've covered so far. So speed to market and lowering complexity of your code base. You'll also need to think about, you need to think differently about how you scale your systems. So that's completely different as monoliths, of course, which is a benefit. And ensure that they are resilient. So architect for resilience. Don't also be surprised if things like distributed transactions, talked about this, or cap theorem start giving you headaches either. The cap theorem, it's like consistency, availability, and partition tolerancy. You can't have all three of them. So mostly what we do is we give up consistency. We make it eventually consistent. Because we want to be available. And we want to have partition tolerancy. If some part of the network goes down, we want to still be able to work. So this is important, and that's why it's no silver bullet and it's not a golden hammer. Okay? I think that's a good way to stop, to end this presentation, and give you the nuanced view of microservices, not the hyped view. All right? All right, and if there are questions, please feel free to ask. Any questions? Serious questions. Nope? Okay. Thanks everyone for your attention.